Hello, in this video I'm going to go over Keto Enol Tautomerization, and I'm going to show you both a base-catalyzed mechanism and an acid-catalyzed mechanism. Okay, and this can happen with ketones. It could also happen with aldehydes or esters, and we would call this the keto form. Okay. And it is in equilibrium over two elementary mechanistic steps, which we'll see in a minute, with, and I got my equilibrium arrows mixed up. The keto form is actually usually the favored form, okay? But it is in equilibrium with this tautomer. We call that the enol. It's called an enol because we've got this CC double bond and we've got this OH group, and those are both functional groups we'd find in alkenes and alcohols. Even though this is the minor tautomer, this can play important roles as an intermediate on the way to products. So let's look at the mechanism of how we can get from the keto form to the enol form. And I'm going to do first the acid-catalyzed mechanism, and then we'll also look at the base-catalyzed mechanism. In the acid-catalyzed mechanism, the first thing that's going to happen, and this is typical of many acid-catalyzed mechanisms involving carbonyl compounds, we're going to start with a proton transfer. And that gets us a protonated oxygen. We can call this an oxonium ion. All right, and we can draw a resonance form for this. We can delocalize that pair of pi electrons onto the oxygen. Okay, and we get that. And then our second step is going to be another proton transfer. All right, so now it's important to know I could do this with either resonance structure. If I do it down here, it's going to be two arrows. Oops, there's a plus charge there. Okay, got to keep that plus charge. If I do it here, there's going to be three arrows because I'm going to take off the proton, we're going to form the pi bond, and then we'll move that pair of electrons onto the oxygen. So you can use either resonance form. Just make sure you use the correct curved arrows. I'm going to do it off of this top one. Okay, so I'm showing a three-arrow proton transfer. I could also show a two-arrow one down here. I don't like to see one-arrow proton transfers. I see that a lot in the textbook, but I like students to know that there is something that is taking that. There is a base that is taking that proton off. Okay. All right, and that's going to get us to our enol. Okay. So there we go. There's our acid-catalyzed enol keto tautomerization. The conditions we would use would be H3O plus and H2O are one possible set of conditions that would do that. Okay. We could also do this under base-catalyzed conditions. So let's look at that. So note with the acid-catalyzed conditions, our intermediate here has a formal or a net overall plus charge. Okay. Okay, so I'm going to start with the same reactant here. Our ketone. All right, and now under base-catalyzed conditions, this is going to be usually, well, it could be sodium hydroxide and water. It could be sodium ethoxide and water, sodium methoxide. We could have alkoxides also. All right, we could have lithium isopropylamide also. All right. Under the base-catalyzed conditions, we're going to deprotonate the carbon first. And the intermediate we get here has an overall negative charge. Okay. And we can draw a resonance form of this. All right. We can carefully draw a resonance form of this. All right, one bond there between the oxygen and the carbon. There we go. Okay. We call this species the enolate ion. And the enolate ion is an important intermediate in a lot of mechanisms we're going to see in this chapter. It's nucleophilic at this carbon, so it can react with a variety of electrophiles. Okay, and at this point, we're one step away from making our product, or our enol form. This is usually not the product we're going after ultimately. In fact, we're usually using the enolate to make something else, not the enol form, at least under base-catalyzed conditions. Under acid-catalyzed conditions, we often make the enol and then have that act as a nucleophile. All right, so there you have it. There's our enol. So we have 2 proton transfers to get us from the ketone to the enol, and under base-catalyzed conditions, our intermediate will have an overall negative formal charge. All right, and that concludes our video on enol keto tautomerization. One other thing I want to say, these are not resonance forms of each other. They are constitutional isomers. Okay, we're breaking this sigma bond. We're making a new sigma bond. These, however, are resonance forms because we're not breaking the sigma bond structure. We're just delocalizing pi electrons. Okay, that's an important distinction. All right, thanks for watching.